start from current slide, but before we get going on that, let me remind you, do any of you have any other classes later today scheduled for Wednesday? None? Well, this won't affect you any. If you know of anyone who does, afternoon today, so 35 minutes after our class is over, the college is closing. Okay, Governor Ivey recognized the July 5th as part of the July 4th holiday, which is fairly unusual, but it's okay. We are closing today at noon. See, we're not working Fridays in the summer anyway, so that meant that regular 5-day-a-week situations, 8 hours a day, that would be 24 hours of a week. And to get our 24 hours a week, since we're doing 10-hour days for 4 days a week, 10 on Monday, 10 on Tuesday, that's 24 today, so that will be closing at noon. Strange statement here, all classes beginning after 12 p.m. on Wednesday, and all Saturday classes will be canceled. Guess what? We don't have any Saturday classes in the summertime. So where did that come from? You would think he may have checked with the instructional office. Of course, he's head of the instructional office. Are any of you taking any of the A&M courses, Alabama A&M courses that are taught on Lawson's campus? You are. Do you know if they're meeting today? You might want to check and find out. Lawson classes are canceled, but that doesn't extend to A&M. So you might want to check with them first. Is a Wednesday class in the afternoon? I'm sorry? Okay, well, so check with them and see. We can't speak for them, but we can speak for Lawson classes. All right, any questions? Anything we've covered so far? All right, let me see if I can find, I'm going to come back to this in a bit. Good white space right there. Okay, we are going to do example 3. And here comes example 3. If there's no questions, let me get my pen set up. Okay. Analyze and sketch the graph of f of x is equal to x divided by the square root of x squared plus 2. Now, again, analyze and sketch the graph. Let's do our analysis first. That's usually a good place to start. What are some things we look for, think about when we're analyzing the graph of a function? One of the first things we ought to consider, what? Earth to class, come in please. Okay. I'll give you a hint. Most of the time we assume all real numbers unless indicated otherwise. What would that be? Anybody? Oh, it's been a long time since Monday, hasn't it? Okay. Thinking about the 4th of July already. Okay. First thing we consider, what is the domain of that function? Okay? Now, what 3 possibilities would limit that domain? You know, that all real number situation. What 3? Why is this in my pocket? I don't know. Okay. Wow. Okay. What 3 situations would limit the domain of a function, keep it from being all real numbers? Okay, if your denominator could be 0. You do have a variable in the denominator, so it's a possibility. Can that denominator ever be 0? No, because x squared, the minimum it can be is 0. Add 2 to it, it's going to be 2. Square root of 2 is greater than 0. You'll never get less, even down any closer to 0 than that. So nothing there. What's the second thing? First is you can't divide by 0. Second, you can't take the square root or an even root of a negative number. Here we have a square root, but as we just said, this thing can't be 0, it can't be negative. The minimum it can be is 2. So that's out of the picture. Okay? What's the third that we've hit so far? Not involved here. Log. A log can neither be 0 nor negative. Okay? We don't have any logs in this one. So the domain here, all real numbers. Okay? So, that's all right. Domain's all real numbers. The range, they like to talk about the range, but usually don't know the range until you do the graph. Okay? Do a little more analysis. So, after domain, we'll worry about range later. What are other things to consider? There's 4 kind of biggies. The what? Okay, the x and y intercepts. Okay, so I'm going to write down, since it's not all that important, domain, all real numbers. I'm just going to put all reals. Okay, now x-intercepts. How do you determine the x-intercept? What's true about an x-intercept? What is equal to 0? No, the function. The function is equal to 0 because you see, x-intercept is where it crosses the x-axis, right? What's true about every point on the x-axis? Y is 0. Okay? And what's your y here? F of x, okay? So where this is equal to 0. Now, in this case, I think what you're thinking about where the denominator was 0, that would be your vertical asymptotes. But we've already determined that the denominator will never be 0. So that's one thing we know right off the top then. Vertical asymptotes, none. Okay? And we know that because the denominator will never be 0. The domain of the function is all real numbers. Okay? So let's get back to laws here. Now we got enough for a volleyball team. Okay. All right. Now, x-intercepts, where y or f of x is equal to 0. What will make the left-hand side equal to 0? The only thing that will make the left-hand side equal to 0. What must be true about the right-hand side? You don't care what's going on in the denominator. For the numerator is equal to 0. Only way y can be 0 is if this numerator is 0, and guess what that means? This is x-intercept. Where's that going to happen? X equals 0, and it happens to be y is equal to 0 there too, which is a dead giveaway that this is also your y-intercept, because that's where x is equal to 0. And whereas you might have more than one x-intercept, not in this problem, you can't have more than one. You may not even have one y-intercept. And since we know x is 0 there, that's going to be a y-intercept as well. Okay? So x equals 0, y equals 0. There's your one and only intercept, both the x-intercept and y-intercept. So there's one other thing we haven't done. We've done x and y-intercept, vertical asymptote. What are we missing? The horizontal asymptote, if there is one. Let's see. Now, this isn't your standard polynomial function, is it? Okay? Now, what is going to be true about the horizontal asymptotes? What gives that away? Remember that Monday was a long time ago. Okay. Ratio of your leading terms. Now that would be if it was polynomials. This isn't polynomials. That's a radical down there. But you can kind of treat x squared, the square root of x squared, as if that was your leading term. And what would be the square root of x squared? X. So this looks like it would be 1. Okay? But there's a catch here. When x is greater than 0, this would be, horizontal asymptote would be 1. When it's less than 0, since that, then your x would be negative, but your x squared is positive, and square root is positive, so that would be positive, it would be negative or positive. So your horizontal asymptotes, in this case, 2 of them, are x equal 1, I'm sorry, f of y is equal to 1 for x is greater than 0, and y is equal to negative 1 for x is less than 0. Now we're talking about the long run, you know, way out there. So we're talking about big, big x's, okay? So that's going to be, you don't have to put equal to 0, because we're not even caring what's happening at 0. We already determined that. That's going to be a x and y intercept there. But in the long run, it looks like this is going to 0. I mean, the y value is going to plus 1 when you're going positive, and minus 1 when you're going negative. All right. That's about, oh no, what are some other things we could do here? This was all pre-calculus algebra stuff. That all analysis right there, pre-calculus algebra. How about, what does calculus lend for us? Enable us to consider. You've been in here all that long? It's the title of the chapter. Applications of differentiation. What does the differentiation tell you? One differentiation. Second? That's the second derivative. First derivative tells us, we'll get there. First derivative tells us, oh boy, Monday was a long time ago. What's your first derivative tell you? Anybody? What have we been taking first derivatives for? Boy. Like in pre-calculus, I said one of the key things you need to know, f of x is equal to y. That's a big thing. Y is equal to f of x. Okay? In Cal 1, one of the biggest things you need to know is the derivative tells you the slope of the tangent line. Come on, we knew that, didn't we? Now, what special values are we most interested in with that slope? These values, those values, are that value. Tear the board down. Where the first derivative is. Help me, somebody. 0 or doesn't exist. What are those values called? Where the first derivative is either 0 or doesn't exist. Given the little symbol C. Second? Not constants. Critical numbers or critical values, okay? So we're interested in that. That's where the first derivative is either 0 or doesn't exist. So what have we got to do before we can determine that? Your Jesus answer? Anybody? Take a derivative. Now, before I want to take a derivative here, I want to make a decision. These are hard sometimes, aren't they? I can take it just as it sits there, and that way I'll be using what rule? Quotient rule. Or I can write that just ever so slightly differently, and then I'd be using a product rule. Which one you want to go with? Second? Product. So how would we rewrite this so we can optimize the product rule? X times x squared plus 2 to the negative 1/2 power, right? Isn't that the same? Okay. I don't like to take derivatives of radicals. I really don't like to take derivatives of things in the denominator. So if I can write it, get the radicals in exponential notation and the things in the denominator in exponential notation, I'm a happier camper. So, how does the product rule work here? What would the first derivative be? Anybody? Help me. How does product rule go? Y'all wanted to use it. How does it go? Anybody? What's the product rule? Boy, only Monday was a long time ago. Last week was even longer, wasn't it? How does the product rule go? Product of two functions here. How do you take its derivative? Anybody? I'm getting the silent treatment today, am I not? Okay. What have I done wrong? Okay. What's the product rule say? Anybody? Please tell me somebody knows, right? Okay, I'll tell you. Y'all are just holding on till I gave in, right? It's the first times the derivative of the second plus the second times the derivative of the first. Or the second times the derivative of the first plus the first times the derivative of the second. It doesn't matter which order you do them, just do them both. So what would this be? How do you want to do it? Gave you two options. Tell me how you want to do it. Second. First is x times derivative of the second, negative 1/2 x squared plus 2 to the negative 3/2 times chain rule, inner part, 2x. Perfect. Okay, there's the first part. First times the root of the second. Plus, plus what? Okay, what's the derivative of the first? Derivative of x. What? Oh, that was easy. And just write down the second then. X squared plus 2 to the minus 1/2. All right, let's clean that up just a little bit. Okay? First way we're going to clean it up is this. Here is a 2 in the denominator and a 2 in the numerator, all within the same thing, all multiplied together. Those go away. And then you got an x times an x, so that's going to be an x squared. There's a minus sign out front over x squared plus 2 to the 3/2 power. Now you could have left it upstairs if you wanted to. I probably should have. I may go back and do that, but just to let you see how it looks. And then this is, I think I prefer it that way. Nothing in the numerator except a 1 over x squared plus 2 to the 1/2 power. Now, what might we choose to do with that? Common denominator, and what would it be?
X squared plus 2
to the 3/2 power. So what would we need to multiply this by to make that x squared plus 2 to the 3/2 power? So again, multiply that thing to the 2/2, and 3/2 plus 1/2 is, 2/2 plus 1/2 is 3/2, right? Well, that to the 2/2 power is the first. So we multiply the numerator by x squared plus 2 and the denominator by x squared plus 2. Do you see how I magically did that? Yay or nay? Okay, makes sense? Multiply the numerator by x squared plus 2. Multiply the denominator by that. That's to the 2/2. Add 1/2 that you already had. Now you got 3/2. So now we can combine numerators. And that would be a minus x squared plus x squared plus 2 divided by x squared plus 2 to the 3/2 power. And what do you notice about that numerator? X squareds add to 0. All right, so here's your first derivative, 2 over that. All right, now how are we supposed to analyze that? We look for places where either this is 0. Any place where that's equal to 0? None whatsoever, okay? Because the numerator would have to be 0, and 2 is never 0, okay? So there's no place where that's 0. How about the other possibility? Where it doesn't exist. Is there any place where that doesn't exist? Basically, we've already been through this argument. The denominator would either have to be 0, which it can't be, or inside the radical, which we have written in radical form, would have to be negative. Never negative, okay? So there's no place where that first derivative is either 0 or doesn't exist. So that means this function is strictly increasing or strictly decreasing. Interesting, right? Now let's just take a quick look and say, which is it? The first derivative is this thing. Is that ever negative? 2 is never negative, and this thing in the denominator is never negative. We've already determined that. The square root of something, principal square root, is positive, and it's not 0. So this is a strictly increasing function, monotonically increasing everywhere. All right. First derivative, we didn't get any critical values, but it still told us something. It's increasing everywhere. Okay? Now, if we combine that with the fact that it's the horizontal asymptote is a -1 here, and you have to go through 0, 0, and a +1 there, I already have a really good idea how that's going to look. I have a great idea how it's going to look. But let's go on, and what should we do next? Second derivative, f double prime of x. Now I'm going to go back and write my f of x as 2 times x squared plus 2 to the minus 3/2 power. Because I prefer dealing with exponential notation than rational function. Okay? That's just my preference. How do you take the derivative of that? Say a little louder. Okay, not necessary. This is just a coefficient 2. If that was a function of x, yes. Not a function of x, it's just a constant. So that's just the power rule. right? How does that work? A little louder. 2 times negative 3 halves, and that would give us negative 3 times what? X squared. Well, yeah, it's going to be that, but let me go and write the x squared plus 2 to the what? It was negative 3 halves, now it goes to negative 5 halves. Okay, good. Now, what you were thinking, times 2x, derivative of the inside. Okay? Now, just rewriting that a little differently, let's combine the negative 3 with the 2x. That would be minus 6x over x squared plus 2 to the 5 halves power. Okay. Now, what do we consider here? We took a second derivative. Why? What are we looking for? Okay, now second derivative gives us someone said it earlier, concavity, either concave up or concave down. Okay? Now, it also gives us where the concavity is. If it's not positive or negative, it can be 0 or same as first derivative, or doesn't exist. Okay, we're interested in those features. Those could be points of inflection where it changes the concavity from up to down or down to up. Okay, so is that 0 anywhere? Yeah, where? When x is 0. Okay? So we have a possible point of inflection at x equals 0. We'll have to determine in a minute. Okay? Now, is there any place where that doesn't exist? Anybody? Any place where that expression does not exist? No, we've been through that before. Okay, numerator's fine, no problem there. The denominator can't be 0, and the radical can't be negative. So, yeah, that's good everywhere. Okay? So, our only possible point of inflection is when x equals 0, but we already know what the function value is at x equals 0. That is our x and y intercept. Now, the question is, do we have a change of concavity there? It may not, there's no guarantee. So let's look to the left of 0, like a slightly negative number, minus 1. What would be the concavity then, minus 1? All I'm interested in is the sign, positive or negative. Positive, which means it's concave up, left of 0. How about to the right of 0? Second derivative is negative, so it means it's concave down. So it is a point of inflection. The concavity does change at 0, 0. Okay? So, let's see what we've got then. If we can make a graph of our function. This is going to be a bit bizarre because I have very little room for it, but let me make as much room as possible. 1, 2, 3, 4, 5, 6, 7, 8, 9. Negative 1, 2, 3, 4, 5, 6, 7, 8. Okay. Positive 1, 2, 3, 4. Negative 1, 2, 3. Okay. Let's try that. Okay. Now, the only point we know is 0, 0. X-intercept and y-intercept at 0, 0. We do know horizontal asymptote when x is positive. Let me put this in red. That's going to be at positive 1, come on back. Come on back. There we go. Too bad. Okay. And when x is negative, less than 0, it's at negative 1. Okay? So there's our two horizontal asymptotes. Okay? There's no critical values. No place where the first derivative is 0. So let's go back and see what the first derivative is at 0. Okay? That might be an interesting thing. What is the slope at x equals 0? Okay? First derivative was this thing right here. When x equals 0, well, no, I'm sorry. I was going to say we didn't ever do our y-intercept. We did. I forgot. Okay. All right. So when x is equal to 0, what's your first derivative? Numerator is 2. Denominator is 2 to the 3/2 power, which is going to be 2 cubed, which is 8. And the square root of 8 is something close to 3, between 2 and 3, right? So this will be something near 2/3. So here your slope is about 2/3. I'm just going to estimate it right there. Okay? Concave up to the left, concave down to the right. So I'm going to make a wild guess that it's something like this, which is what I would have guessed before. I just didn't know what the slope was here. The slope at 0 was something between 1 and 2/3. Okay? So it may be a little steeper than that. There's our graph. Only 1 point, folks. Okay? But concave up here, concave down there, point of inflection right there. The slope there is about whatever 1 over the square root of, 2 over the square root of 8. You can plug it into your calculator and see what that is. Something between 1/3 and 1, right? Yeah, closer to 1/3. 2 over the square root of 8. Oh, I messed that up. Wait. Messed that up. I just squared this. No. 2 cubed, square root of 2 cubed, square root of 8. What is 1 over the square root? Oh, 2 over the square root of 8. It's 1 over root 2. Yes, I know that. That's 0.7. Yeah, I knew that. 0.7. 0.707, blah, 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 right? Okay. So I underestimated a little bit. Not more. About 0.7. Any questions?
What did the second derivative tell us?
It tells us whether the function's concave up or concave down, or point of inflection, where it changes its concavity. That can occur just like the first derivative. You look at where it's equal to 0 or doesn't exist. You could have a point of inflection at either one of those. You may not, but it could be. That's where you investigate. And here we did have one, because it was concave. It was negative to the left, positive to the left, negative to the right, so therefore it had to have a point of inflection there. It changed its concavity from up to down. Okay. So that's what it tells you. Without, and it was 0 there. We determined it was 0 there, the second derivative. But we knew the first derivative wasn't 0 there, so I knew it didn't have a 0 slope there. See, that could have been another point of concavity if it was concave down here and then concave up beyond there. But then you would have had a first derivative being 0. This one wasn't, so, and we already knew it was concave down here, concave up here, and concave down there. That's what the second derivative tells us. Okay. Any questions? All right. In the book, they really expanded the graph because they had a lot more room than I did, but they really overemphasized here because notice in the book, they basically changed their scales pretty wildly. Here is one there, and there's one there, you know. One unit here is real close on the x-axis, one unit on the y is really far. But there, you sure enough, you have a slope. It's hard to tell the slope here because they changed the scales. But that slope should be about 0.7. It looks like it's greater than 1. It really isn't because they expanded the scale there. But that's what you got. Concave up here, concave down here. Had a change in concavity. Second derivative equals 0 right there, 0, 0. No horizontal asymptotes, no places. I'm sorry, no zero slopes. Local max or min is a constantly increasing function. Monotonically increasing. Okay. Any questions on that? All right. Let's move to example 4. Okay. We'll use the same slide here. Example 4. Analyze and sketch the graph of f of x is equal to 2 to the 5/3 minus 5 to the, 2x to the 5/3, leave off my variable here, minus 5x to the 4/3. Not one you run into every day. What might be some things we need to consider? It's the first thing we considered before. Domain. Any restrictions to the domain here? All real numbers. Why could you say that so confidently? Okay, there's no x's in the denominators. I agree with that. But what's other things we have to consider? Yeah, there are. Anything to the fractional power has a radical. But what radical would that be? Both of those are. In the denominator you have 3's. So these are cube roots. Any restrictions on cube roots? None whatsoever. If those are square roots, whoa, watch it, folks. You got to consider those. These are odd denominators, no restrictions. You can take the cube root of a positive number or a negative number or 0. You can take the cube root of any number you want to. So you're absolutely right. There's no restrictions here. And, of course, there's no logs in it either. So all real numbers is your domain. Okay? Oh, on that last one, at the end of the problem, we could have said, what's the range between -1 and 1? Not including, but only between -1 and 1. No way, I don't think you could look at the problem to begin with and say, oh, there's the range. No. You have to almost graph it first. There were indications, but usually after you graph. All right, so we've done the domain here. And I'll give you a hint. This is going to have, the range is going to be -infinity to +infinity here, all real numbers, because this is acting a lot like a polynomial. And polynomials have no limits on range, okay? I say that with some confidence. I think I'm right, okay? So, even though you can't really, I think you can say on this range. What next? Second? X and Y intercepts. Now, where is the what is true about an x-intercept? Okay, the y is equal to 0. Now, if y is equal to 0, that means, I'm going to write it in radical notation, 2 times the cube root of x to the 5th has got to equal, if that's 0, then this would be 5 times x to the cube root of x fourth. Now, since you have cubes on both sides, you could turn around and just cube both sides. And I don't think you have any problem with that. But this would be, if you cube this, that would be 8x to the fifth is equal to, ooh boy, 125 x to the fourth. Everybody follow what I did there? Okay. Now let's write it back on one side. 8x to the fifth minus 125x to the fourth equals to 0. What might you do with that? Factor out an x. And what does that leave you? X to the fourth, sorry. And what does that leave you with? 8x minus 125. And that product is equal to 0. Now, what are the two possible values that would make that 0? X equals 0, certainly that would work for that one. And that's actually a repeated root 4 times. Okay? Now, let's think about that root. Repeated root 4 times. Okay? When it's a single root, it just crosses the x-axis. When it's a double root, it kisses the x-axis. A triple root kind of hangs around the x-axis but finally crosses. A fourth root comes down, hangs around a long time but then goes back up. So it still just kisses the x-axis, doesn't cross it. So at x equals 0, we figure you're going to have that kind of behavior. Now you don't know if it's from above or from below, but you're going to have that lingering behavior but going to go back in the same direction. It's not going to cross the x-axis at x equals 4. I don't think. We'll see. What's the other possibility?
125 over 8.
Yes, x equal 125/8, which is one of my favorite numbers of all time. That's that's exactly equal to 1 15 5/8. Okay, I don't usually write them that way, but just so I'll know where to put it on the number line. Okay, so x-intercepts at x equals 0, but I really need a point there. If x is equal to 0, what's my y? 0, so 0, 0. We've also found the y-intercept, okay, because that's where x is equal to 0, okay, well, that's the y-intercept as well. Okay, and the other x-intercept is at, when x is equal to 125/8, we now have to figure out what the y value is. Oh, joy. Okay, someone pull out a calculator here, okay, and enter into that. Now, if you prefer doing a fractional number, that would be 15.625, if you want to use that, okay, but whatever. 2 times 15.625 raised to the 5/3 power minus 5 times 15.625 raised to the 4/3 power equals. See what your y value is there. Wait a minute. Oh no, that's right. Wait, we already know. That's the y-intercept. I mean, x-intercept. The y is 0 there. Sorry about that. I was doing something else. Duh. Better be 0. If it's not, we got some big problems here. So that's x-intercept. We've already found our y-intercept, happily. Okay? Now, what are the other things we usually consider? Okay, horizontal asymptotes. I think I've already given that away in that this is a lot like a polynomial function which comes in late. I know that it means it rhymes here. Okay. All right. So, Well, we lost one and gained one, so we're still at 6, just enough for a volleyball team. Okay. I think I already gave this away. This function acts a lot like a polynomial function in that it doesn't have any, okay, number one, there are no places where it doesn't exist. And here's Jalen. All right, we're slowly getting a decent class here. No places where it doesn't exist, so there can't be any vertical asymptotes. And if it's acting like a polynomial function, that means there aren't any horizontal asymptotes. It increases without bounds one way and the other way. Okay, we just don't know which way yet, or we kind of do. Okay, so horizontal asymptotes, we're going to guess none. Okay. Because that would be ratio of leading terms. We don't have any leading terms. Okay, vertical asymptotes, because there's no place it doesn't exist, none. So we don't gain a lot there. We found 2 x-intercepts, and at the same time, one of those is a y-intercept. Okay, so what might we do next? Yes, all right, good deal. Now, just so I can save on space here, we've already done the calculation. I wrote the answer here. Let's go on and take this. I probably could erase that part too, but I'm probably going, I don't know. Let's go on and erase it too. Okay. Just in case we need it later, need the space later. So, you said take a derivative. So, tell me how to do that. F prime of x is equal to? Somebody help me. And what would that give you? Ten-thirds, right? Times x to the 2/3, isn't it? Right. Am I right? 3/3 from 5/3 is 2/3, okay? Minus (20/3) times x to the 1/3. Perfect. Okay. Oh, here's Terry back. Good. All right. Now, why would we take a derivative in the first place? Yes. It tells you the slope. And what special values are you looking for the slope? For the first derivative is either equal to 0 or doesn't exist. Okay? Any place where that first derivative would equal 0. When x equals 0 is pretty obvious, okay? So set this equal to 0, and we know x equals 0 will be one place. We know that the y value there is going to be 0, okay? The question is, are there any other places equal to 0? We'll go through the same argument we did before. If that's equal to 0, that means that 10/3 x to the 2/3 is equal to 20/3 x to the 1/3. And what was our step we did before? Cube both sides, and this is really getting to be nasty looking. Okay, when you cube this, you get 1,000 over 27, right? X squared equal, and cubing that one, I believe, is 8,000 over 27. X. Okay? By that? Okay? Pull it back across. Factor out what we can. I know we can factor out a 1,000 over 27. And that would give us, and an x. Go on and pull an x out too. And that gives you x minus 8 equals 0. Now, I did several steps at once there. Are y'all okay with that? No? Okay with it? I subtracted that from both sides. You got 1,000 over 27x squared minus 8,000 over 27x. Well, I knew 1,000 over 27x is going to be a common factor with both of those. To pull that out, I left an x here and a minus 8 there. That went back to being 0. Okay? Now, as you already guessed, x equals 0 is a 0 for that. What's the other 0? There? Is there another 0 here? X equals 0 would be a 0, or x equals 8 is a 0. So x equals 0 is a 0, and x equals 8 is also a 0. So those two potential places for critical values. We don't know that they are, but we suspect, well, we know they have to be one of those two places. Are there any places where that first derivative is not defined? Remember, this is our first derivative. Anywhere where that's not defined? No. Everything's in the numerator. There's still cube roots. No problem with cube roots anywhere. None are in the denominator, so yeah. So there's no place it's not defined. So those are our two potential extrema. Either maximum, minimum, or neither. Okay, we'll have to determine if it's going to be a neither. Now, that gives you an x value. I need a y value. I already got the y value for 0, 0, 0. We already know that. We need to find the y value for x. So this point will actually be 0, 0, which is the same point we have for our x-intercept. This point, however, is going to be x equal 8, and what's your y value? Now you go back to the original function there. All right, now this one's not as bad as it seems. If you plug in an 8 for the x, that 3 in the denominator means a cube root. Cube root of 8 is 2. 2 to the 5th is crank. 2 to the 5th, 32. 2 times 32, 64. Okay, cube root of 2 again, cube root of 8 again is 2. 2 to the 4th is 2 to the 5th was 32. 2 to the 4th is half of 32. 16. And 5 times 16 is what? Okay. Goodness, my brain's going bonkers on me. 5 times 16 would be 80? Yeah, 80. Okay. And 64 minus 80 is negative 16. So there's our y value, negative 16. Okay. So we have our two potential critical points. Okay. 0, 0, which is our x-intercept and y-intercept, and now is also a potential critical point. And the other potential critical point is 8, negative 16. Now, by the way, I didn't say this when we were there, that second x-intercept, we know it's only crossing there. It can't be touching and kissing because that was a single multiplicity of 1. This is multiplicity of 4 here. Oh, I've already erased it. Yeah. The first one was multiplicity of 4. That one's multiplicity of 1. So it's got to be crossing there. Don't know which way it's heading, but it's got to be crossing there. We suspect which way it's heading. Okay. So, what might we do next? Hint, we took the first derivative. Yeah, let's take the second derivative. Okay. F double prime of x is going to be what? Someone help me out here. All right, you did well on your first test where you took, or second test where you took derivatives. What's the second the derivative of that one? Second? 20 over 3 times 3 is 9 times x to the negative 1/3, whoa, 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 minus not that hard, 20/9 times x to the negative 2/3. Okay, so we've taken a second derivative. What do we do with it? Second? That's going to tell us that ultimately, but what do we do with it? Why did we take it? We're going to find concavity. You're right. What values around which might we find concavity? We need to know where. Okay, now that is your first derivative. We know we have two potential extrema, one at 0, 0, and one at 125. No, I'm sorry. One at 0, 0, and one at 8, negative 16. Okay. Now, just looking at those, that looks like that's got to be a maximum if it's going to change direction there, because it's going downhill after that. Okay? And we're going to have the place that crosses the x-axis in between, because remember it crossed at, what was that? That was 15 and 15.625 over that point. Forget that. Okay. Yeah. So we actually know more than we think we do. Okay. So, okay. Let's get back to this. What are we going to do with second derivative? Same answer to what we did with the first derivative. Either set it equal to 0, or where it doesn't exist. Okay? So, let's do each of those. Now, I'm going to go back and write this in radical notation, I think. No, I'm going to leave it in this. Okay. So, this will be 20/9. I think I'm going to write it in without negative exponents. Okay. 20 over 9 times the cube root of x. I went over and did it both. Minus 20 over 9 times the cube root of x squared. And we're going to set that equal to 0. Okay? Now, oops, I didn't put my cube root in. Okay. Now, trying to figure out whether it's going to be better to move that to one side of the equation or the other. We did that the first two times. Let's do it again, I guess. It really doesn't matter. Let's do it. So that would be 20 over 9 times the cube root of x equal 20 over 9 times the cube root of x squared. Now, what's one thing you notice you can do? Yeah, get rid of your coefficients because they're the same on both sides. Multiply both sides by 9, divide both sides by 20, they're gone. So that gives you 1 over the cube root of x equal 1 over the cube root of x squared. Okay? Now, what might you do? What do we do before? Get rid of the cube root? Cube it. Okay? And this would be 1 over x equal 1 over x squared. Okay? Now, yeah, let's go back to the same side. 1 over x minus 1 over x squared. Set equal to 0. And what might you do there? Okay, 1 over x. Actually, you could do that. That's a very legal move. However, what I think I want to do is first get least common denominator. So to make this an x squared here, make that an x. So now we have x minus 1 over x squared is equal to 0. I think that tells us a little bit more. Number one, it tells us where is that equal to 0? At what value of x? Yes, x equal 1. So we have the second derivative, f double prime equal to 0 at x equal 1. Okay, that's where the second derivative is equal to 0. Is there any place that second derivative doesn't exist?
X equals 0.
Oh, yes, it can't exist at x equals 0, can it? Okay, so f double prime of x does not exist at x equals 0. That's pretty interesting, isn't it? Okay. Interesting. Okay. I really didn't see that one coming. All right. We'll buy that. All right. Now, we need values there. We know x equals 0. This is the point 0, 0. Okay. We've had that in every case here. Something seems a little bizarre here. Yeah, that's absolutely right. Okay. But at x equal 1, we haven't determined that. What's the value of the function there? Go back up here, and at x equal 1, what's your function value? Go back to your original function. X equal 1, y is equal to? Really easy. Anybody? When x equal 1, y is equal to? -3. There it is, -3. Because when x equal 1, the cube root of 1 is 1. 1 to the 5th power is 1. So that would be 2 minus cube root of 3 is, cube root of 1 is 1. 1 to the 4th is 1. 2 minus 5 is -3. All right. Now, that took all the space we had and then some. All right. So let's gather all that information together. We got that at the top. Let's add what we got here. 0, 0 is also a critical value. The book calls them critical numbers. I like critical values. It doesn't matter. We also have a critical value at 8, -16. That's a critical value. And we have this right here is also a potential point of inflection. We don't know that it is or not, but we'll call it point of inflection. We'll put a question mark there. Okay, and then at 1, -3, we have a point of inflection. Potential. Okay. We don't know for sure, but we think so. Okay. Now, we need to hang on to our first and second derivatives. So I think I'll leave those in place. And let me erase everything else. Okay? I sure hope I won't need any of this again. Now the reason I need to hang on to our first and second derivatives, especially the second derivative, we might need that to do some evaluation. And I think I'll take this one out of there too. Boy, this takes a long time, doesn't it? Analyzing these graphs are not trivial, but they're not impossible. I mean, you just do the same things, but you just have to be a good bookkeeper. Keep up with what you're doing and register it well so you can find it. Okay, so let's set up our axes here. Now, we know we're going, this is 15 point something in a 625. The minus is going to a -16 down there. So we're going to need, let's say at least 20. So let's put a 20 here. Try to get an equal 20 over here, -20. And down here, let's do a -20. And up here, we'll try to do an equal 20. So that makes this -10, this 10, this 10, and this -10. Okay? And this will be 5. I'm trying to get all the points we'll need. That will be a 5. That will be a 3 here. I need it down here. That's a -5. So this will be a -3 down here. We need a 1. So that's a, well, it's all 7 or 8 of them at least, don't you think? Just kidding. There'll probably be at least 1. Okay, I would guess. Okay, I think we may have everything we need. Let's first get our y-intercept, 0, 0, x and y-intercept. Another x-intercept out here, so that's 15, 17, 18, 16. So just short of 16 here, somewhere about right in here, there's our other x-intercept. Okay? 1, -3 is a potential point of inflection. So 1, -3 will be down here. Now, it doesn't really need a point, but that's a possible point of inflection. And the other one, a critical value at 8, -16. So there's 7, 8, somewhere about in here, -16, there's -15, so about there would be -16, somewhere about there where that thing's in my way. That's a potential critical value. This is a critical value. Okay. Now, Remember, this also was a critical value here too, wasn't it? I think I erased too much, didn't I? Yeah, 0, 0 is a critical value, potential critical value. Okay. Now, what we need to know is what's going on over here. Because we don't have anything over here. We need to know, is this function increasing or decreasing? We know it's got an intercept there. We know it's got a potential critical value there. And we know it's also got a potential point of inflection there. So we need to know as much as we can about what's going on there. So let's do the first derivative at, say, -1. So if you put a -1 in here, what's the cube root of -1? -1. Square that, you get a +1. So you get 10/3. Okay? Now, put a -1 in here. Cube root of -1 is -1. And -20/3 times -1 is +20/3. So, that tells us this is positive, that's positive at -1. So therefore, this is an increasing function here. So if it's increasing to the left of here, that means it has to be down here somewhere. Now we could plug in a -1 here too, that would work. -1 here would be -1 to the 5th power is -1. 2 times that would be a -2. And -1 to the 4th power is +1. So -5. So -2 minus 5 is -7. So yeah, we've concluded that down here at -1, -5, you're down here at -7. Okay. So we've got another point there. Okay. You know the point's there. You know it's increasing there. You know it has a 0 slope there. And remember, that was at 0, 0, that was a multiplicity of 4. So you know it can't cross the x-axis there. So it must be coming up incredibly rapidly here. Okay. And have a 0 slope there. Okay. Now, let's do our second derivative there at -1. So f double prime of -1. Cube root of -1 is -1, so that's in the denominator. Well, it doesn't matter where it is, -1. So this will be a -29ths, and cube root of -1 is -1, but you square that, and you get a +1, -29ths. So your second derivative is negative there, which is concave down. And my graph here was showing concave down. It had to almost, to have a 0 slope there, it had to be concave down. So it's concave down on this side. Let's go to the right-hand side, where x equals 1. Well, we know the value here is a -3, right there, so it has to be going downhill. Sure. That was a multiplicity of 4 there. It had to be going, it couldn't cross the axis there. But let's see what the second derivative is there. F double prime of -1 would be, no, a +1, sorry, would be 29ths, and then the cube root of 1 squared. That's 29ths minus 29ths, okay? That says it's another 0, and we didn't wind up with a 0 there, did we? Did we miss that one? Let's go back to what we had there. We had 1 over the cube root of x equal 1 over the cube root of x squared. Yeah, we had 1 as a possibility. Yeah, we knew that. That's a point of inflection. Duh. We needed something to the left of that. Sorry. That is a point of inflection. Okay? We need it. Shucks. At 1/2. I hate that. Let's choose something even better. Let's choose 1/8. Okay? Because you're doing cube roots, it's easy to take a cube root of 1/8. So let's do f double prime of 1/8. That would be 20/9 times 1/2 minus 20/9 times 1/4, because you're squaring 1/8. Yeah. Okay. So obviously this gives us a positive number there. So positive number, that's concave up here. So this is bizarre. It's concave up here, which is really strange. So it's concave down on this side and concave up on this side. So there, at that point there, even though the first derivative is 0 and you have a curve, the concavity changes. So it is a point of inflection. Okay? So it's concave up here, concave down there, and then it changes again here, or we think it does. Oh boy, what a mess. Okay? There's just so many things, and my graph is so small, it has to be spread out there. Here's a couple of things. You know this has to be a minimum, because it's positive here, negative here, positive there. So this has to be a minimum here, okay? All right, and here it's just passing through. So this is how it looks. Concave down here, concave up here. I guess at that point there is at x equal 1, -3, it is a point of inflection, they say. Okay? So, at 0, 0, undefined relative maximum. No, it says it's concave down on both sides. I must have made a mistake there. Concave down on both sides and concave up on both sides here. There's your point of inflection where it changes from concave down to concave up, and it's concave up for the rest of the time. Whew. That one really was a pain. Okay. If I had more paper, more space, I think it would have been a lot easier to do, but it's such big numbers in it, it's really hard to graph. All right, let's clear that one. Any questions before I clear it? And let's do example 5. Now, example 5 is one you can go to larsoncalculus.com for an interactive version, so if I screw this one up, But this one I think is pretty easy. Well, knock on wood. Analyze and sketch the graph of this one. F of x is equal to x to the fourth minus 12x cubed plus 48x squared minus 64x. Okay. What kind of function is that? Polynomial. What can you tell me about its domain? All real numbers. Okay. No denominators, no radicals, no logs, all real numbers. How about its range? This is a little trickier, but not too bad. You know it's going to go to positive infinity because this is a fourth power. That means when x gets very large negative, you're a very large positive. X is a very large positive. Y is very large positive. So it's on the up and up. So there's not going to be any limit going upward. There probably is going to be a limit going down. We won't know that until we do more analysis. Okay? But we know on the upper end it's going to positive infinity. So domain from minus infinity to infinity. Range, we don't know about the lower side, but it's going to positive infinity on the upper side. We know that. Okay. Now, what's the next thing we look for? X and Y intercepts. Okay, that sounds good. Do you think there's going to be any horizontal asymptotes? No, because this is going to positive infinity, both positive and negative. Can't have a horizontal asymptote, okay? Think it has any vertical asymptotes? No, because it's defined everywhere. There's no place where it's not defined. So horizontal asymptote, vertical asymptotes, none, okay? Does everybody see why that's true? If it's a polynomial function, it's going to be going to infinity in both directions. Can't have any horizontal asymptotes. Okay? Vertical asymptotes only exist where the function is not allowed. It's allowed everywhere, so there's no vertical asymptotes. So now let's do, did you say x-intercept? That's supposed to be that. Okay. X-intercept. What are we going to have to do that? Set it equal to 0. Okay? Now, what's the first thing you might think of doing here? Factor. What can you factor out of every term? A little louder? X? Is that what you said? Okay. And that leaves you x cubed minus 12x squared 48x minus 64 equals 0. Now, this takes you back to good old pre-calculus. Oh, what's 1, 0? Anyone know a 0? X equals 0. And what's the y value there? 0, 0 is an x-intercept. Now, flashback to pre-calculus algebra. Okay? We're going to have to find the zeros of this. And I don't think you can factor by grouping and get anything that works, because this is 12 times that. That is not 12 times that. So you're not going to be able to factor by grouping. Now, does anyone remember Descartes' rules of signs? Remember the name maybe, but not anything else. Well, what it tells you is that if you count the number of sign changes in the polynomial, you'll know how many possible positive real zeros you have. Where you have 1 sign change, 2 sign change, 3 sign changes. That means you have 3 or 1 positive real zeros of this. 3 or 1. got to have 1 because this winds up being a cubic. It's going like this. So it's going to have to cross the x-axis at least once. Okay? Now if you do the f of, I'm just looking at this one now. F of minus x, this will be a minus x cubed, minus 12x squared, minus 48x, minus 64. No sign changes there. There aren't any negative zeros. So don't even bother looking for a negative real zero of this one. Okay? If you have any, there's going to be either 1 or 3. They're all going to be positive. Okay? Now, does anyone remember the next little trick we used? It was something called the rational zeros test. Anyone remember how that goes? You look at the ratio, rational, of the constant term to the leading coefficient. So that's 64 to 1. So all your rational zeros are going to be multiples of 64. So they could be plus or minus 1, plus or minus 2, continue. Will 3 work? No. 4? Yeah. 5? 6? Plus or minus 8. Okay? Now, and after that, they're getting too big. Okay? So let's try each of those individually. Now, the easiest way to do that is our good old synthetic division. Remember that? Probably not, huh? Well, let's take one of them, like 1. Well, 1's easy. You don't need synthetic division. If you put 1 in for each of those numbers, each of the x's, then you just have your coefficients. 1 minus 12 would be minus 11, plus 48 would be plus 37 minus 64. That's not a 0. So don't worry with plus 1. It's out. Okay? But don't worry with minus 1. Because remember, Descartes' rule of sign says you don't have any negative real zeros. So let's go to 2. Now we'll do synthetic division. 2, and remember how you do synthetic divisions? Write down the coefficients. 1, negative 12, 48, and negative 64. Now, always count how many numbers you have. 4 should be 1 more than the number of your degree. And it is. So you haven't skipped any terms here. Skip a line, draw a line, bring down the 1, and then start multiplying and adding. 2 times 1 is easy. 2. And minus 12 plus 2 is negative 10. 2 times negative 10 is negative 20. And add, you get 28. 2 times 28 is 56. That's not going to work. 2 doesn't work. Okay? Let's next try 3. 1 was out. 2's out. None of the negatives are going to work. Let's try 3. Whoa, I didn't mean to do that. I want to put them that far out. Okay. Oh, 4. I'm sorry, 4. 3's not an option. Okay, multiply. 4. Add. Multiply. Add. Add. 16. Multiply. 64. Ding, ding, ding. We have a winner. Okay. X equal 4 is another 0. Okay. Now, what's the value of the function when x equals 4? I think someone's going to have to pull out a calculator. I'm not going to do this one in my head. 4 to the 4th power minus 12 times 4 cubed. I should know that one. 64. Plus 48 times 16 minus 64 times 4. Was it?
It's 0.
We knew that, didn't we? What was I doing? That's the 0 of the function. Yeah, we knew that. So y-intercept at 4, 0. That was completely useless information. I mean, we knew that. That's what we were looking for. But what do we have left? What we have down here represents x squared minus 8x, I can't read, plus 16 equals 0. What might we do with that? Any ideas? We can factor it. And what does that factor as? X minus 4 times x minus 4. Guess what? 4 is a triple root. Okay? You got 3 all at the same values. So, now a triple root, remember, multiplicity of 3 is going to cross the axis, but it's going to hang around there a little while. So it acts like a cubic function and sort of hangs around, but then moves on up. X equals 0 is a single root, so it's just going to cross there. And basically, we could almost draw the function right now. I think I could. Okay? 0, 0 is a 0, and 4 is 0. So let's make that my 4, 2, 1, 2, 3. Okay, that's the 0. Okay? I know it's on the up and up. Okay? So, and I know here it's going to cross, and here it's going to come up, hang around, and cross. But we don't know the minimum value. Okay? So what are we going to need to do to get the minimum value? Oh, did we do? Oh, we already know. This is also our y-intercept. Is 0, 0 as well. Okay, take a derivative. All right, so let's go back. This was all the work to get our zeros, and we only wound up with 2 of them. We thought we could get, remember Descartes' rule of sign said 3 or 1? We got 1, okay? Well, we got 3, but they were all 3 the same one. So I'm going to leave my graph there because I'm going to fill in the blanks later. Okay, hope to anyway. Let's take these out. Okay. Go back to the original function and take our derivative. I wish I'd have thought of this before we started the problem. Anyone need a break? Because we're over halfway through. Do you? Yeah? Yeah, I think we need to stretch or do something. Oh my. Anyone need this up a little longer? I'll save on the bulb. I'm going to run down to the restroom myself. Get up, move around, get the voice flowing. Wake up! No, or something like that. too many. I forgot to turn off the projector, sorry. I turned off the projector. I forgot to put a hold on the thing. So for anyone listening, there's a big, long, dead place. I forgot to turn off the recorder. So let's just get back to it. Now, what was the next phase we were going to go to? We determined the domain, at least half the range. Determined there were no horizontal asymptotes, no vertical asymptotes. X-intercepts, two of them, one's a triple, one's a single. Found the y-intercept was one of those x-intercepts. So what's our next step? Take a derivative. Now, you tell me, you rather take the derivative of the original form or the factored form? Original for sure. Who wants to do a product rule when you could just do a straight power rule basically thing? So f prime of x is equal to, help me, 4x cubed, help me, next, minus 36 x squared
Plus
96x minus 64. Now, what possible values are we most interested in those derivatives?
where it equals 0,
Or
where it doesn't exist.
is there any place this doesn't exist? No, it's a polynomial function that exists everywhere, so we're only interested in where it's equal to 0. Now, what's one thing that you might think of to do before you do anything else for that? Factor out a 4. Okay, so let's divide by 4. That will give us x cubed minus 9x squared come on, 24x. Isn't that 1 4 short of 100? And 25 fours and 100, so it'd be 24 fours, right? Minus 4 into 64, 16, right? Yay? Okay. Now, no way to factor that by grouping, so that's out of the picture. So I guess we have to go back to good old Descartes' rule of signs. How many possible zeros do we have here? 1, 2, 3, or 1. Same as before. Okay. Let's try 1 first. Okay. And negative zeros will be none. Okay, so you either got 3 or 1 possible zeros for your first derivative. Let's try 1. 1 minus 9 is minus 8, plus 24 is, isn't that minus 16? Okay, do it this way. Add your negatives together, or positives together. 25, add the negatives together. Minus 25. 1 is a 0. Ding, ding, we've got a 0 here. So x equal 1 is a 0. Now we need to know a value there, so go back to the original function. We did that earlier, and I don't remember what we came up with. Here we have a 49, and here we have a minus 76. And that's what? 25? So at 125, did I do that right? I don't remember having that number before. minus 12 plus 36. No, that's not right. No, it's minus 11. Yeah, that's why it wasn't right. Minus 11 plus 37. Maybe that's 27, is it? The old gray cells ain't what they used to be. 76, 49, 17. 27, yeah. 127. There is a potential extreme value, a critical value. So let's go on. If we do our synthetic division with 1, we'll do 1 minus 9, 24, minus 16, degree 3, yeah, everything's fine. Bring down the 1, that'd be 1, minus 8, minus 8, 16, 16, 0. We knew that was going to be a 0, but what we did, we needed to know what was remaining. And this is x squared minus 8x plus 16. Is that the same thing we had before? I believe it was, wasn't it? And what were our roots here? X minus 4 times x minus 4. So again, we have a double root here, but this is a different reason, okay? This is where your first derivative is 0. So x equals 4, okay? So that's going to be at 4. Now this one we need to plug in, but we did that, didn't we? Isn't this 4, 0 again? Yeah. So we don't need to put, wait. Yeah. 4, 0 again. So there is a possible extreme value. Not definite, but possible. Okay. Well, let's see. Yeah. In fact, I'm pretty sure it's not going to be 1. Okay. Now, what next? So let's see. Critical values will be 1, 27, and 40. So 40 is a x-intercept. It's a possible critical value. Let's continue. What's that again? It's a negative 27? You're absolutely right, isn't it? Okay. So let me erase most of this. In fact, we don't want this anymore either, I don't think. That's a minus 27, okay, because here it is. 49 minus 76 is minus 27, not positive 27. Okay. So what are we going to do next? Anybody? Take the second derivative, f double prime of x, and what will this be? Anybody? 12 x squared minus, second, 72x plus 96. And what do we do with that? Okay, we set it equal to 0, or where it doesn't exist, it exists everywhere, so we set it equal to 0. And now factor in what will come out of each of those. I know a 12 will. What will that leave you? X squared minus 6x plus 8. And you can divide out the 12, so it's out of there. Will that factor? Both have to be negative. Two numbers that multiply to be 8, add to be 6. 2 and 4. Okay, so x equal 2, x equal 4. Those are potential points of inflection. We need to figure out what the values are there. I think someone did this for me before, but I didn't write it down. So go in and plug in. Oh, we know x equal 4. Guess what? POI, points of inflection, 4, 0. It's an x-intercept. We know potential critical value, potential point of inflection. Okay, it is a critical value, but potential extrema and potential point of inflection. We need to figure out what x equal 2 is. I mean, what the value is when x equal 2. So someone plug in. 2 to the 4th is 16 minus 12 times 8 would be minus 96. So that would be minus 80 plus 48 times 4. I'm getting tired of doing this in my head. Someone do it on a calculator. That would be 2 to the 4th is 16 minus 96 plus 48 times 4 minus 128. Do it however you want to. Okay, I was trying to say some steps. Plug in x equal 2 into this. What do you get?
Negative 16.
Second?
Negative 16.
Negative 16. All right. Now, let's see what we got, folks. X equal 1, you're way down here at minus 27. So obviously this is going to be a minus 27 downhill. And that is where we were expecting it to go. Okay. At 2, negative 16, that would be somewhere right about there. So that's a potential point of inflection. So yeah, this I'm convinced this is going to be a minimum there. Okay. And then 4, 0 is going to be everything else. So we're going to come up here through here. I can't get my pen to write. Okay. Come here, hang around there, and keep on flying north. Okay. Now, concave up here, concave down there. Point of inflection. Concave down here, concave up here, point of inflection. And this is just a 0 there. So I think we got it. Without any other mess, they do a whole table, but this is what it's going to look like. Okay? 2 zeros, and the Descartes rule of signs would have said we either have 4, no, we have 1, 2, 3 changes of sign. Well, we have 3 zeros, 1, 2, 3. That's 2 zeros there. It's a double 0. You have to count them twice. Okay? 1 relative minimum. This is not an extreme value. The first derivative is 0 there, but it's not an extreme value. Okay? It's a point of inflection that doesn't have an extreme value there. So only one extreme value, an absolute minimum here. So we can fill in now. We go down to negative 27. Range negative 27 to positive infinity. You're not going to tell that until you do the analysis. Okay? There's no way you can look at that and say, oh, yeah, it's going to have a minimum of 27. You can't do it. I can't do it. Maybe you can. Okay. Concave up everywhere here, concave down here, concave up there. Okay, so that pretty much does it for you. Two critical values, one is minimum, one is not. It's neither minimum or maximum. Two intercepts, one y-intercept, same as that one. 2 points of inflection from concave down, up to concave down, concave down, concave up. There we have it. And you can do analysis of the rest of it if you want to. Not necessary. We basically have it all in our graph there. On the up and up, we knew that had to be the case. Yeah. Perfectly fine. Okay. All right. One more of these. Okay. Let's do one of a trig function. Analyze and sketch the graph of, pretty exciting, isn't it? F of x is equal to cosine x over 1 plus sine x. All right. First thing we consider, look for, think about, what's that? The big D. Domain. Okay, and what interests you about a domain?
This one will be all the numbers except when the denominator equals 0.
And when the denominator equals 0, you're absolutely right. So what we have here, what you just said, is 1 plus sine x, I don't know if you realize you said that, cannot equal 0, right? When is that true? Well, let's subtract 1 from both sides, and we'll say sine x cannot equal negative 1, right? Where is sine x equal negative 1? No, half pies, okay, it's half of your half pies. It's your, okay, 3 halves pies, but not 5 halves pie. Not 1 half pie, because it's positive 1 there. 3 halves pies, yeah. 5 halves pies, no. 7 halves pie, yeah. So it's half of your half pies, the one. So let's just do them. They don't, because it has a period of 2 pi, we can restrict our analysis to any interval of length 2 pi. They say for convenience, let's go from negative pi halves to 3 halves pi. That's a little bizarre. I would say let's go, just to cover everything, negative 2 pi to positive 2 pi. So that's what I would say. And where is that? So at x equal minus pi halves, 3 halves pi, minus 3 halves pi, that would be it. Between, no, not minus 3 halves pi, minus 5 halves pi. That would be outside then. I think that covers all of them, isn't it? Yeah, I think that would do it. That's why they chose those two, but that's not a good choice. You're limiting yourself to exactly that. So anyway, those are the two values where, so we'll say between consider an interval of minus 2 pi to 2 pi, okay, then the values in here where it does not exist, the domain within that would be from minus 2 pi to minus pi halves, and from, open parentheses there, union minus pi halves to 3 halves pi, and then from 3 halves pi to 2 pi. And we'll close there, but you'll see the pattern in that. Okay. So now we found the domains, the values you can't have. So that also tells us our vertical asymptotes. As soon as you know this, then you know the vertical asymptotes are x cannot equal minus pi halves and 3 halves pi. Now you can be a little more specific there because the period is every 2 pi. So you could say minus pi halves plus 2n pi. That covers all of them. 3 halves pi and all the rest of them, but that would be all of them. This is only in this interval we chose. But minus pi halves plus 2n pi, that covers them all. So there's your vertical asymptotes. That would be a description of your domain. Set of all x's except for these x's here. So negative pi halves plus 2n pi, that covers all the ones that you cannot allow. Okay? And that'll be your vertical asymptote. Okay? Now, let's not mess with range yet. I think we'll see. Because you have vertical asymptote, the odds are you got something going to infinity in one or both directions. So probably not going to have a limit on range. At least that's my guess right now. Now I've seen the graph, so I know that's true. All right, what next? We've already determined vertical asymptote. Think we're going to have a horizontal asymptote? With trig functions, this is really hard to tell. Polynomial functions, yeah. Trig functions, let's don't even worry about horizontal asymptote until we see what happens. And generally, if you have a bunch of vertical asymptotes, how can you have a horizontal asymptote? It's just not going to happen with a periodic function. It's just not going to happen, okay? So we won't mess with that. Horizontal asymptote, we'll go say none. What's the next two things we consider? Okay, not yet. We'll get there. What have we not considered yet? Yeah, x and y intercepts. Okay? So x intercepts. Where is your function going to equal to 0? The denominator will never make your function equal to 0. Only your numerator. And where is cosine x equals 0? At every half pi, right? Is that right? Yeah, the cosine is 0. So x-intercepts are at all the half pi's. Except the ones that it's not defined. Okay? So these will be at the other half pi's. So this will be at negative 3 halves pi, 0, and at negative pi half, no, positive pi halves, 0. So the easy way to express this one will be at x equal pi halves plus 2n pi. And every one of those will be a 0. Okay? So every other half pi is your vertical asymptote, and the ones in between those are your zeros, which we'll see is true too. Okay? Y-intercept. What's your y-intercept? What's true about a y-intercept? X equals 0. Plug in a 0 here, and what do you get? 1. Okay. Got it. Now, I think we got everything we can there. Now, I heard people clamoring for first derivatives. How do you want to do this? Quotient rule or product rule? Huh? You have a preference? It doesn't really matter. Product rule? So how would you write this? Cosine x times 1 plus sine x to the minus 1. Okay? So what's your first derivative? How does that go? Second.
Oh wait, no, never mind. It's the first times the derivative of the second.
First times derivative of the second, so that'd be cosine x times derivative of minus 1 times 1 plus sine x to the minus 2 times chain rule, derivative of the inside is cosine x, isn't it? Derivative of sine x is cosine x. Agreed or not? I think I'll put those in big brackets. Okay. So that's the first time derivative of the second plus what?
Second times the derivative of the first.
What's the derivative of the first? Negative sign. So this is going to wind up being a minus as well. So that'll be sine times 1 plus sine x to the minus 1. Okay, now I'm going to go back and write this as rational expressions and see what we get. In the numerator, well, we have a minus sign. That comes out. We have a cosine squared x over 1 plus sine x squared. Then we have a minus sine x over 1 plus sine x to the first power. Right? Now what do we need to do to that to clean it up a little? Yeah, common denominator, which would mean squaring this one, meaning multiplying it by 1 plus sine x, and multiply the numerator by 1 plus sine x. Okay? Now what do we have now? Minus cosine squared x minus sine x minus sine squared x over 1 plus sine x squared. Now, notice anything we can use to simplify that? One thing I kind of like to do anyway, they're all minuses in the numerator. Let's just make that a minus out front and do a cosine squared x plus sine x plus sine squared x over 1 plus sine x squared. Okay, now what do you notice you have in the numerator now? Anybody notice anything? Those of you who were in my trig class had better notice it.
It's
Pythagorean identity, sine squared x plus sine squared x is equal to what? 1. So what we have now is a minus, I'm going to write it this way, 1 plus sine x over 1 plus sine x squared, which of course will be a minus 1 over 1 plus sine x. Now, what are we interested in here with that first derivative? Either where it's 0, is that ever equal to 0? The only way this fractional form will ever be 0 if that numerator is 0. Is 1 ever 0? Never. Okay? Or where it doesn't exist, but where it doesn't exist is where the function doesn't exist. It doesn't exist at those half pies, minus pi halves, and every 2 pi from there on. So those don't count as first derivatives as critical numbers because the critical number must be in the domain. Those numbers were already excluded from the domain, so there are no critical values. Okay? None. No zeros and no places where the first derivative doesn't exist that are also in the domain of F. Okay? So no critical values. Next. Okay, what does that mean? If there's no places where the function is changing direction, that means it's going to be monotonic between these asymptotes. And the graph will show you that's indeed true. There aren't any places where the first derivative goes to 0 or doesn't exist, except at those asymptotes, which of course it doesn't exist there. So it's going to be monotonic there. Now, if it's okay with you, I'm going to erase everything but my answer. Okay? Is that all right? Because I don't have enough room to work. So I'm going to erase all this. I hope you got it all first. Sorry, I should have said that before I started erasing. Okay. I'm going to bring this up and say minus 1 over 1 plus sine x. Okay. Now I'll erase it down here. Okay. Now, what this tells us, no critical values. No places where that's equal to 0, and no places where it doesn't exist that are in the domain. No critical values. So what do we do next? Take a second derivative. F double prime of x. And on this one, I think I want to rewrite that to be minus 1 plus sine x to the minus 1. Is that okay? Yay or nay? All right to do that? Okay. Take the second derivative. Okay, you said cosine on top? Or what did you say? I didn't hear.
I was going to use the product. Wait, no.
Okay. -1 times -1 is 1. So 1 plus sine x to the -2 times chain rule, second, cosine x. Okay, got it. So this will be cosine x over 1 plus sine x squared. There's your second derivative. What are we interested in? Where that is either 0, any place that's going to be 0? Every one of those x-intercepts at the half pi's that are in your denominator as being vertical asymptotes. So that would be at pi halves, at -3 halves pi, and all the ones that would be your the ones we said, where was it, up here, pi halves plus 2n pi. That's exactly it. Your x-intercepts, okay, equals 0 at pi halves plus 2n pi. Exactly your x-intercepts, same as this, okay? Any place it doesn't exist? Same places we excluded to begin with, our vertical asymptotes, okay? So that's not in your domain, so no, there aren't any additional ones. Okay, so we have potential points of inflection at your x-intercepts. Okay. Now, what I'm really tempted to do is this. Do you remember when we did trig identities and that was everybody's favorite? Oh, I remember that so well. F of x is equal to cosine x over 1 plus sine x. If we were trying to simplify that, we multiplied the denominator by its conjugate, 1 minus sine x. Well, if multiply the numerator by 1 minus sine x, that's legal then. Okay, so this would be cosine x minus sine x cosine x, right? Numerator. Denominator becomes 1 minus sine squared x. And what's 1 minus cosine? 1 minus, I'm going to go back and do something that I should have done. Shouldn't have separated those in the first place. Leave it as cosine x times 1 minus sine x. Okay? Now, what is 1 minus sine squared x? Cosine squared x. And now you have a cosine x 1 over cosine x. Which now, and here's why I did that, this is the same as secant x, 1 over cosine x, minus tangent x. I thought that was going to give us something worthwhile. It doesn't. Sorry. It was an effort, but it didn't pan out. I was hoping it was going to give us something like some multiple of code, and you might be able to do something with it, but I'm not going to chase it any further. So Say again? I can't hear you. Okay, I won't. I had thought that might produce something nice, but it didn't. So let me get rid of that. It's just going to be in the way. It's all true, but it's not helpful. Okay. Like I said, it probably would if you pursued it, but I'm not going to pursue it because Ryan told me not to. Okay. Now, let's see what we've got. All right. We've got okay. We've got vertical asymptotes at minus half pi. Oh, let me go back. Label my things. I'll put them here. This is yuck. Okay. This is pi halves, pi, 2 pi, 3 pi, and so on. Minus pi halves, minus pi, minus 2 pi, minus 3 pi, even a minus 4 pi out here. And we're just going to make this 1, 2, 3, minus 1, minus 2. Okay. Now I go and change my colors. Okay. Vertical asymptotes at minus pi halves, and then every 2 pi from multiple of that. So there's half a pi, pi, another half pi, there's 1. 1, 2, 3, 4, there's 1. 1, 2, 3, 4, there's 1. 1, 2, 3, you can't do the next one. Okay? So, we've got that. We've got our zeros. Oh, the y-intercept at 0, 1. So let's put that in there. 0, 1 right there. And your x-intercepts at your other half pi's. There, 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 and there. Okay? Now, we have no local minimum or maximum because we had no critical values. Okay? Now, we have points of inflection at these same, the same as our intercepts, okay, x-intercepts. What we need to do is find out where they're increasing and where they're decreasing, and I think this one gives it away right here. The fact that this value is here, you must be going to a positive infinity there, you must be passing through this value, and then going to negative infinity there. And then because it's a repeating function, it has to do the same thing between every intercept. And went off scale. Now, are these points of inflection? Yes. Concave up here, concave down there. Every one of those is a point of inflection because you change your concavity. You can't help but change the concavity, okay? So that's basically what your function looks like, and if you look in the book, that's what you see. What I was trying to do with my aside there was trying to see if that came up to be a phase shift of a cotangent function. but it doesn't show that to be very obvious. So just leave it like that. Now, that finishes 3.6. Finally, okay? Now, you were asking about, are they on the test? There will be, if my memory's right, at least 2 of these on the test, but all you're asked to do, maybe I have work to get there, find the very things we look for. Find the x-intercepts if they exist, the y-intercepts if that exists, the vertical asymptotes if those exist, horizontal asymptotes if those exist, and concave, the intervals that the function's increasing and decreasing, and the places where you have points of inflection. And then whether it's concave up or down. Yep. So you'll have several things to answer, but you don't have to draw the entire graph, though that certainly would be helpful. So let me say this. There will be at least one that all it's asking for is to sketch the function. Okay? So I'll provide a piece of graph paper for that, but if you want more graph paper, you can either ask me for it or provide it yourself. But I think that doing the graphs will be beneficial to answering the questions. And since you need to show your work, I think that would be a good thing. But anyway, homework exercises here. I would do all 4 of 5 through 8. Now, only 5 and 7 are in the back of the book and at calcchat.com, but these are matching problems, so you should be able to do 6 and 8 as well as 5 or 7. But they're both at CalcChat. Then do any of the odds 9 through 35. They're all at CalcChat. 33 is at CalcView. Do any of the odds 37 to 43. They're all at CalcChat. 37 is at CalcView. Do any of the odds 45 to 49. They're all at CalcChat. Do 51. It's a CalcChat. Either 53 or 55. They're both at CalcChat. 53 is at CalcView. And then I think you can do 57. They say you might need computer algebra system or something else, but see if you can do it without it. If you can't, don't sweat it unless you got it. Okay, exploring concepts, you can do any 59 through 63 if you choose to. That's up to you. Either 65 or 67, and all 59 through 63 should be at CalcChat. 65 or 67 should be at CalcChat. 69 should be at CalcChat. Any of the odds 71 to 75 should be at CalcChat. 77 should be at CalcChat. You can think about doing either 79 or 81. They should both be at CalcChat. 83 or 85 are both true false. You should do those if you'd like. They should be at CalcChat. And then either 87 or 89, they should both be at CalcChat. 91 should be at CalcChat, and 93 should be at CalcChat. All right. Now, I'm all in favor of skipping 3.7. It's a great section, optimization problems. Are any of you going into industrial engineering? You are. You might want to look at that section because a lot of stuff that you do in industrial engineering deals with optimizing. So even though these are shapes and things like that, you still might want to take a look at that section. I don't know if any of the other majors do that much optimizing. You might, but industrial engineering, that's one of the things you do. That is 3.7. I'm sorry, I was saying 8.7. 3.7. These are dealing mostly with shapes and other things. You would be dealing with industrial processes. What's that? Because we don't have time to cover it. And this is a very long section. A very long chapter. So we need to move on. And you're the first industrial engineer that I've run across, so sorry about that. The ones that I think might need it the most. Okay. Let me clear my screen here and make sure. Oh, yeah. here we are, still in Chapter 3, Application of Differentiation, and we're jumping to 3.8, which is Newton's method. Now, I would have thought, if this guy had to develop calculus from scratch, which he did, he had some help from friends. He communicated with others, he built on other people's work, but basically built it from scratch. Do you think he would have had time to go through and find out methods to apply this? I would have guessed no, he's too busy developing. No, he came up with probably the quickest method for finding zeros. No one's found anything better than him. He developed calculus and then did an application no one's been able to match since, okay? And that's what we call Newton's method. We'll approximate a zero of a function using Newton's method, okay? The technique for approximating the real zeros of a function. Now, remember what we were doing? We were first doing Descartes' rule of signs, and then doing rational zeros test, and then doing synthetic division, trying to find them, and hoping we could. Okay? Well, that works if your answer is a rational zero. Or one of your last two answers is any real number. Newton's method does it no matter what they are. Okay? The technique for approximating real zeros of a function is called Newton's method. It uses the tangent lines to approximate the graph of the function near its x-intercepts. To see how it works, consider a function f that is continuous. Boy, if you have a discontinuous function, don't even try it. Okay? They don't work. A function that is continuous on some interval a to b and differentiable on a to b. You can't use it if you're using the tangent line. You've got to use the derivative. So it has to be differentiable on the open interval a to b. Now, if f of a and f of b differ in signs, so f of a could be negative, f of b positive, or f of a positive, f of b negative. If they differ in signs, then, by the intermediate value theorem, f must have at least one zero on the interval between a and b. Why? Because it's a continuous function. And if it starts up here and ends down there, it's got to cross there somewhere. Or if it starts down here and ends up there, it's got to cross the x-axis somewhere. So it's got to have at least one zero on the interval if it's a continuous function, which we assume, and they have opposite signs. Okay? Now, to estimate that zero, let's just pick a value, x equals x1. Okay? Something between a and b. Okay? F of a is positive here, f of b is negative here. Okay, so we'll pick some x equals x1. Just somewhere between a and b, probably not right there. Okay? Shown in the figure. Newton's method is based on the assumption that the graph of f and the tangent line at x1, f of x1, both cross the x-axis about the same point. Okay? So it's saying that the graph of f and the tangent line are going to cross at about the same point. Okay? There are cases where they don't, and then it doesn't work. Okay? But you see, if this is your function, it's positive here, negative there, so the odds are it's going downhill somewhere in between. I mean, it's got to, right? So the tangent line is going to be going down here. Well, the intercept has got to be somewhere between that, and the tangent line is going to be somewhere relatively close. Definitely, you wouldn't expect to be right on it, but close. Okay? So, draw that tangent line and make that your x2. Then go down and find f of x2. It's down here this time. Draw its tangent line, and it's going to be something like that. That's even closer to C. Then, just keep doing that, and they'll zoom in. Those tangent lines are going to get closer and closer until you get within some tolerance there and say, hey, that's close enough. Okay? So that's the deal. because you can easily calculate the x-intercept for that tangent line, that's not a hard thing to do, you can use the second and usually a better estimate of the 0 of f and the tangent line that passes through the point x1, f of x1 with a slope of that, okay? In the point slope form, the equation for the tangent line is y minus f of x1 is equal to f prime of x1 times x minus x1, and all these things. So y is equal to f prime of x1 times x minus x1 plus f of x1. All these things are pretty easy to calculate, okay? And then you plug in the value and estimate. You get a new estimate and go, so let y equal 0, okay? Set this equal to 0, and then set this, so why did they move it over here anyway? So f of x1 will be approximated, or minus f of x1 will be approximated by that, okay? So what you get down to solving for x. Let's go back and do that. They flip this things, they leave out steps, okay? Now, in point slope form, this is the equation of the tangent line. We want to know where that crosses the x-axis. That's where y is equal to 0. So what we have here is then f prime of x1 times x minus x1 is equal to minus f of x1. Okay, I just moved it to the other side. Okay, so this is f prime of x1 times x minus f prime of x1 times x1, okay, is equal to minus f of x1. Solve for x. So we have f prime of x1 times x is equal to f prime of x1 times, I'm going to put the x1 in front so you don't get confused. Well, jumping ahead too soon. Okay. Minus f of x1. Okay, I just moved that to the other side. Now divide by f prime of x1. Okay, so this goes out here. It also goes out here, and it leaves you that. What do we have? You have x1 minus f of x1 over f prime of x1. That's what your x is equal to. Let that be your x2, and just keep going. Every time you do it, calculate f of x2, f prime of x2, take x2 minus that ratio, that becomes your x3. Then do the same thing over and over. So this is what your x becomes, x1 minus f of x1 over f prime of x1. So from the initial estimate x1, you're saying a new estimate, which we're going to call x2. And then all you do is calculate f of x2, f prime of x2, and then subtract from x2 that ratio, okay? And every time, and this just shows what happens, here's your first derivative, drop down, and there's your f of x2, then that next derivative pulls you here, then f of x3 is going to be here, that next one's going to almost put you directly through C. And if you want to get closer, you just keep going until you zoom in on it, okay? And Newton's method works so rapidly. Now, Have any of you ever used the graphing calculator to find the zeros of a function? Hopefully you have. Guess what? You're using Newton's method. No one's come up with anything quicker than Newton's method. It is the fastest, most efficient way of finding those zeros. At least in my mind. I don't program those computers, so I can't say that, but the last I heard, that was it. Okay? Now, you can improve on x2, calculate a third estimate. x3 will be x2 minus the ratio of f of x2 to f prime of x2. Keep doing it, and all you have to do is just calculate all you do, you have the function, okay? Take the derivative of the function, and then just every time you get a new estimate, plug it in, the function, the derivative of the function, do the ratio, subtract it from. You're going to do this every time. Now, if you ever get that first derivative being 0, that means you've reached the place you're never going to hit the thing again. But you see, if you start well, you'll never hit that. Okay? Say again? I can't hear.
I said we need to do an example.
We will. We're coming up on it. So repeated application is called Newton's method, and here's the technique before we do the example. Newton's method for approximating zeros of the function. The f of c equals 0. In other words, here is some value c that we know is a 0. We just don't know what c is, okay? Where f is a differentiable function on an open interval containing that point c. Then to approximate c, here's the steps. Make an initial estimate x1. Hopefully it's going to be fairly close to c. A graph may be helpful there, okay? Determine a new approximation. And you know in your graphing calculator, when you're trying to find the zeros, it says make an estimate. You give it some value you think is fairly close to it. Once you do that, then it just starts this process and does it. Okay? So, I think you're sort of leaving out the stuff there. Make an initial estimate that's close to C. Now, what I would put in is 1A here. Take the derivative of F. Okay? You already know what F is. F is some differentiable function, so you can take the derivative, take its derivative. Then determine a new approximate, well, then I would also say plug x1 into F and plug x1 into its derivative. Take the derivative, plug x1 into the function, plug x1 into the derivative. Then determine a new approximation. It's x1 minus f of x1 over f prime of x1. That makes your new approximation x2. To get x3, then do x2 minus f of x2 divided by f prime of x2. To get x4, you just go from there. Now, when your difference between one approximation and the next approximation is within desired accuracy, 0.001 or something like that, you say, that's going to be close enough, that's all I want it to, then let that last estimate serve as your final approximation. Otherwise, go back to here and keep getting finer and finer until you get within 10 to the minus 5 or whatever. You know, it's not going to take long. Each successive application of that procedure is called an iteration. So you do as many iterations to get as close as you want to get. Okay? You wanted an example? Here's an example. Do we have time for it? Huh? 3 minutes. Let's do. I think we can. Okay. Calculate 3 iterations. He wanted one. It's all Ryan's fault. I mean, he said, "Give me an example." I'm going to give you an example. Okay. Thank you so much. Okay. All right. Calculate 3 iterations of Newton's method to approximate a 0 of f of x is equal to x squared minus 2. Use x1 equal 1 as the initial guess. Okay? What have you got to do first? Second? Yes, take a derivative. F prime of x is equal to 2x. Got it. Now you're made in the shade here, folks. If x1 is 1, then f of 1 is what? F of 1. Negative 1. Okay? And f prime of 1 is? Second? 2? Is that what you said? Perfect. Okay? Everybody agree? All right. So your x2 is going to be 1, x1, minus f of 1, which is a minus 1 over 2, f prime of 1. So this is 3/2, right? 1 plus 1/2 is 3/2, or 1.5. I don't care what you call it. Okay? Got it? So that's your x2. What's your x3? It's x2 minus f of x2 over f prime of x2. So that's going to be 1.5 minus, plug in that here, 1.5 squared is 2.25. Okay, so that would be 2.25 over, and 1.5 times 2 is 3. Pull out your calculator. 1.5 minus 2.25 divided by 3. 0.75. Okay, so x4 is going to be 0.75 minus, and do 0.75 squared minus 2. Do that quickly. 0.75 squared minus 2. .75 squared minus 2 divided by 1.5. Okay. I think we're off somehow here. Something not working properly here. Our second iteration didn't come out right. Okay. And we're out of time. So we'll pick up on this one next time. We'll use Newton's method, but that gave you the method. Somebody's not doing a calculation right, or I said it wrong or something. Okay. Pick up and go from there. We won't do any new exercises there. Oh, and when we do finish 3.8, we got 3.9 to go, and then we'll be ready for our next test. So that means early next week, probably Monday, we'll be ready for the next test. One more assignment. I forgot to make it. Have a great 4th of July weekend. I don't think I got yours graded. I was grading on them yesterday, but I ran out of time. I'll try to get them finished grading and maybe even out on Blackboard over the weekend.
Oh, I don't know. It won't let me.
Huh?
I mean, when I log in Blackboard, I'm not in this class.
I can't hear you.
I'm not in this class when I log on Blackboard.
You're not in this class?
No. The class isn't showing up on my Blackboard.
You're kidding me. Your name's on the roll.
Yeah.
Okay. I bet you she's not in today. I went by her office yesterday. I was going to go see Jamie Glass, but I went by her office twice yesterday, or 3 times, and she never was in. So she may be off this week. So next week, remind me, and we'll go see what's happening there, because it should be, hey, I wish you'd have told me sooner, yeah, but we'll take care of it next week. Thanks.